Hello everyone, my name is Ramón Ferri and I am presenting today our research on the use of weighted models in propensity score adjustment for mitigation of the self-selection bias in non-probability surveys. So let's start from the beginning. We want to study populations characteristics using a sample. Traditional methods have been considered to provide accurate and representative samples, but in the last few years they are experiencing several issues, such as coverage errors, increases in cost, or decreases in response rates, which have favored the rise of new methods, such as online and smartphone surveys, and other sources for obtaining samples, such as data lakes used in big data. These new methods entail many advantages in terms of cost, response rates, and questionnaire possibilities. However, they are usually administered in a self-selection manner. This is the case for snowball sampling, for online opt-in panels, or even email surveys. This means that the researcher has no control on the selection of the sample. And regarding big data, such as the analysis of social media users, the extraction of large datasets is often linked to data availability rather than probability sampling. Hence, we can encounter the same sort of problems. In a probability sampling design, all the individuals of the target population have a known and non-null probability of being selected in the sample. If any of these conditions do not apply, we have a non-probability sample. These sort of samples can lead to selection bias if the sample population is different from the non-sample population. This is something that was described in Elliott and Valiant in 2017. Some adjustment methods have been developed in literature to mitigate selection bias produced in non-probability samples. Their application depends on the amount of auxiliary information available. Commonly, a probability sample from the same population is available, maybe from a government survey or from another survey from another organization. In that case, we can apply propensity score adjustment or statistical matching. Both of them are based in predictive modeling, but the former models the probability of participating in a non-probability sample, and the latter models the target variables values for individuals in the reference sample. We are focusing today in propensity score adjustment. From now on, PSA. The necessary settings for PSA are these. We need a non-probability sample, a reference probability sample with some design weights, and then an indicator variable that indicates whether an individual belongs to the non-probability sample or not. This is the variable R. In a non-probability sample context, we assume that each individual of the population has a probability of participating on it, called propensity. We consider the case where the probability is conditional to a given matrix of covariates. In practice, we don't have the actual propensities, so we can estimate them by combining both the reference and the convenience sample and building a model M to predict the indicator variable given a set of covariates. The fitted probabilities for each individual are the propensity estimate, and it has to be said that this vector of covariates must have been measured in both samples. Typically, these propensities are modeled with logistic regression equations, although some recent works propose machine learning classification algorithms for this task. Estimators of linear and nonlinear parameters using propensity score adjustment have been developed in literature, using the propensity to construct weights to be used in Harvey-Thompson or Hayek estimators, or even in equilibrium equations. Weights can be calculated just by inverse probability weighting, even with some correction to just stop considering those individuals in the non-probability sample to be part of the target population of the probability sample, or even by more sophisticated procedures such as propensity stratification weighting. In all cases, the use of design weights in the model fitting step, the design weights are available from the reference sample, has been treated differently across the existing works that use propensity score adjustment. Many of these works fit the propensity estimation models considering no weights at all, although sometimes the design weights can be incorporated afterwards using the correction factor that we have described in the previous slide. Some works have even considered to use weighted models, where the individuals from the non-probability sample are assigned unitary weights, and the individuals from the probability sample are assigned the design weight with a correction factor. These procedures have been proven to provide biased estimates of the population parameters. So, in this context, Chen, Li, and Wu in 2020 developed a consistent and unbiased estimator of linear parameters by maximizing the pseudo likelihood function, this one here, with respect to the vector lambda of parameters of the model. If a logistic regression model is used to estimate propensities, then this vector lambda is equivalent to the regression coefficients of the model. And in that case, if the overlap between both samples is negligible or the sampling fraction is small, then this same solution can be approximately achieved by fixing unitary weights for individuals in the non-probability sample and design weights for individuals in the probability sample. So we train a weighted logistic regression model with these weights, and its solution is approximately equivalent to this one provided by the pseudo likelihood function. In several contexts, especially those that involve machine learning classification algorithms, the combination of the probability and the non-probability sample can lead to class imbalance problems if any of the samples is significantly larger than the other one. One of the two possibilities to tackle this imbalance is to train weighted models using unitary weights for individuals in the non-probability sample and the quotient between both sample sizes for individuals in the probability sample. So in this work, we try to compare these approaches. So in order to evaluate the behavior of these weighting procedures, we prepare a simulation using data from the 2012 edition of the Life Condition Survey. We bootstrapped the original sample, which was composed of 28,000 individuals after filtering, up to a pseudo population of 1 million individuals. For each iteration of the simulation, a reference and a convenience sample were extracted. We considered two situations for the reference sample: a stratified cluster sampling design, which was dependent on the autonomous communities and the households, and an unequal probability sampling, which was dependent on the outcome. This design allowed to evaluate the behavior of the estimators under complex survey designs. For each case, convenience samples were drawn with unequal probability sampling according to this formula, which takes into account the age, the computer accessibility of the household, the gender, and the population density. 300 iterations for each sample configuration were simulated, calculating in each one two population parameters related to purchase power. Logistic regression, as well as three machine learning algorithms that allow the practitioners to use weights in the modeling step, were chosen to calculate propensities. These machine learning algorithms were feed-forward neural networks, random forest, and support vector machine. Also, three different procedures were performed in the model fitting step: no weights at all, balancing weights, as described in the previous slide, and design weights as developed in Chen, Li, and Wu in 2020. So, the results of a relative bias for the population proportion of households with a car can be seen in this image. Relative to the baseline is this dashed line here, which represents the relative bias of the unweighted sample, so just the sample mean of the non-probability sample. We can see that using design weights, which is this yellow bar here, provide little gains or even losses under the stratified cluster sampling design for the probability sample. While in the case where the probability is proportional to the income, then the use of design weights improve the relative bias of the estimates for each predictive approach in comparison to the other two approaches, where we use no weights, this is the purple bar, and balancing weights, which is the red bar. We can see that for all cases, for all algorithms, the use of design weights provide a smaller relative bias. If for the case of the mean square error of the estimators, we can see that they follow the same pattern. In this case, the inclusion of design weights in the model fitting procedure can lead to significantly worse estimates under the stratified cluster sampling design and significantly better estimates under the sampling design proportional to the income, especially for logistic regression, GLM, and random forest, Ranger here. We can see that in both cases, the yellow bar is much smaller than the other two bars and also smaller than the baseline. The relative bias in the estimation of the mean home expenses follows the same pattern as in the previous variable, but in this case, the use of design weights under a stratified sampling design also provide less biased estimates, while the other two options have a strongly similar impact. However, This is not the case for the mean square error. When applying design weights in model fitting under the stratified cluster design, estimates are only more efficient than the other two options in the case of random forest. We can see here that for Ranger, when using design weights, the solutions are more efficient than the other two options, but in the rest of the algorithms, they are more or less the same, or even worse in the case of super vector machines. Again, in the case of the probability sampling is proportional to the income, then the inclusion of design weights in model fitting provide much more efficient estimators, especially again in the case of logistic regression and random forest. We can see that when using design weights, then the mean square error is much smaller than the other two bars. In conclusion, the use of design weights provide good results when the sampling design of the probability sample is related to the target variable. We have seen that before. We can see that when the design weights are related to the income, which is a variable that is also related to the target variables of this experiment, then we can see that the inclusion of design weights was much more fruitful, while in the other case, when it was related to autonomous communities and households, which are not related to the outcome in some cases, then the results are much worse. Machine learning algorithms can be considered for propensity score adjustment with design weights in case they admit model fitting with weights, although the estimator's theoretical properties are to be studied because logistic regression is focused on this procedure that optimizes the pseudo likelihood function, but in the case of machine learning algorithms, the loss function can be different. The empirical results that we have seen here show that they are most sensitive to design weights relationship with the target variable. And in the case of we are comparing all of the modeling approaches, we can see that they perform similarly. But when the optimal case for each one is considered, this is the configuration of weights that performs the best for each algorithm, then we can see that logistic regression and random forest perform better than neural networks and super vector matches. So here are the references, the most important reference of this work, and thank you very much for your attention.